Hello everyone, welcome to the seventh lecture of the lecture series on open channel flows. In this lecture, we are going to start our discussion on uniform flow in open channels. So, an open channel flow is called uniform when the flow properties, particularly the depth of flow, remains constant over the course of the flow. So the depth of flow remains space invariant during its course. In the figure at the top, on your left hand side, you can see cross section of an arbitrary natural open channel, and on your right you can see a longitudinal section of the open channel showing the channel bottom and the water surface. So you can see in the figure that the flow is taking place where the flow depth remains constant. So this is an example of a uniform open channel flow. Now you can imagine one thing, that uniform flow is possible only in case of prismatic channels. We have already discussed about prismatic channels in the beginning of this lecture series, and we know prismatic channels are those channels for which the shape of the channel or the bottom slope remains constant. And of course, uniform flow is possible only in prismatic channels. For non-prismatic channels, uh, the depth of flow may vary during its course, and thus the uniform flow, the flow will deviate from being uniform. And if the discharge in the for the flow is constant, then to maintain the mass continuity, the mass continuity statement is given by the equation Q equal to A into V. That's the product of cross section of flow into the mean velocity. So to satisfy the mass continuity equation, you can of course conclude that the velocity will also be equal at different sections of the flow in the longitudinal direction. So in this figure, we can see two sections, 1 and 2. So the velocities will of course be equal at sections 1 and 2. So V1 will be equal to V2 will be equal to capital V. So also you can, looking at the figure, you can of course conclude one more thing, that as the depth of the flow remains constant, so the water surface for a uniform flow will remain parallel to the channel bottom. In other words, the slope of the water surface here will be parallel to the channel bottom slope. As we know that for open channel flows, the water surface represents the hydraulic grade line or the piezometric surface. So the slope of the hydraulic grade line of course will be equal to the channel bottom slope here. And we have seen that the velocity, the longitudinal velocity at different sections are equal. So here the total energy line will also be parallel to the water surface as well as the channel bottom. You of course know that total energy line is the total energy is the sum of the total energy head is equal to the piezometric head and the velocity head. So given that the velocity head is constant throughout the channel length, so here the total energy lines will also have a slope which is equal to the slope of the water surface, which again is equal to the slope of the channel bottom. Also note one important fact, that here the uniform flow, when we mention uniform flow, by default we here mean a steady uniform flow. For the case of open channel flow, unsteady uniform flow is a practical impossibility, since unsteadiness in the flow generates non-uniformity. You can imagine that if the flow becomes unsteady in the channel, the depth and the velocity will vary in time, and of course the variation will with time variation of depth or velocity with time will generate non-uniformity, or the depth or the velocity at different section will change as well. So now our motivation is to derive an equation for open channel flow, for uniform flow. So with that motivation, we can invoke the momentum equation here and analyze the momentum and forces on the control volume as shown in the figure on your right. So in that figure, we can see two sections again, sections 1 and 2, the control volume is shown by a dotted line. We are going to analyze forces and momentum on that control volume. So the momentum equation when applied on the control volume gives us P1 minus P2 plus W sine theta minus F with subscript small f is equals to M1 minus M2. So here on the left hand side we can see all the forces that's acting on the control volume. P1 and P2 are the hydrostatic pressure forces that is working at sections 1 and 2. The friction force here, the resistance force or the shear force, is given by F, capital F with a subscript small f, and this is the shear force offered by the channel boundary as a resistance towards the flow. And of course the main driving force of the flow, as we discussed in the beginning of the lecture of this lecture series, that the main driving force of open channel flow is the gravity force, or the component of weight working along the channel, and W sine theta is that component. It's a body force. So on the left hand side we account for all the forces, and on the right hand side we have momentum fluxes at sections 1 and 2 given by M1 and M2. Now as the flow is uniform here, or the depth of the flow is constant over its length, so the hydrostatic pressure forces are equal to each other, or P1 is equal to P2. Also note that the momentums M1 and M2 are also equal, as the mass flux and the velocity at section 1 and 2 remains constant. There is no difference of mass flux or momentum or velocity at sections 1 and 2. So given that, the momentum also becomes constant over the length. So we are only left with two terms in the equation, in the momentum equation, which is given by W sine theta minus FF equals to 0. Now the weight of fluid in the control volume, inside the control volume, is given as rho g, capital A into capital L, and the friction force can be given as tau naught P into L, where capital A and capital P are the cross section and perimeter of the flow. These are also known as, in open channel flow, these are capital A and capital P are also known as weighted cross section and weighted perimeters. And tau naught is the resistance or shear stress offered by the channel boundary. So Substituting these terms in the previous equation, we can arrive at the expression of shear stress given by tau naught equals to rho g a by p into sine theta, or gamma into a by p into sine theta, where gamma is of course the weight per unit volume. Since for most of the channels that we encounter, the open channels, the channel bottom slope is rather small. That is, theta varies. Theta is mostly below 10 degrees. So for such a small slope, we can approximate sine theta as equals to theta equals to tan theta, and tan theta is of course the slope of the channel. So we can substitute the sine theta by the slope of the channel, that is S naught here. And also the term A by P is an important term in context of open channel flow, and this is called the hydraulic radius of the channel. So hydraulic radius is a length parameter which is a representative of the channel characteristics. Hydraulic radius is a ratio of the channel flow cross section to the weighted parameter, and of course both of them represent the channel flow characteristic. And hydraulic radius plays a very important role in developing many flow equations for open channel flow. So here, applying the above simplification, we can arrive at the equation with an expression of the shear stress given by tau naught equals to gamma into R into S, which is the first equation of the slide. Remember from our discussion of pipe flows before that the bounded shear stress can be defined in terms of the Fanning's friction factor. This we discussed in the component of pipe flow in this course, and in which we have shown that the shear stress tau naught or the boundary shear stress can be given given as half into Cf into rho into V square. And we also discussed that this is a form of the velocity squared law, which says that the any resistance towards a fluid flow is proportional to the square of the velocity, and not proportional to the linear velocity, but square of the velocity. So we have now two expressions of the boundary shear stress given by these two equations, and if we equate them, we can arrive at the equation shown here, given by capital V equals to root under 2g by Cf into root under R S naught, or which can be further simplified as capital V equals to capital C into root under R S naught. This is actually a very popular equation in for uniform open channel flow. This is called the Chase's equation, and this is a resistance formula. What do we mean by that? Since we used in the derivation of this equation, since we used the momentum equation in combination with the shear stress or friction equation, so this is a form of a resistance equation. Remember that in pipe flow, the Darcy-Weisbach equation was a form of a resistance equation. So here, this equation highlighted in blue, which is very popularly known as the Chase's equation, is a form of a resistance formula or resistance equation. So of course, this equation is named after its proposer, who proposed it in the year of 1775, a French hydraulic engineer, Antoine de Chasy. So the formula contains a coefficient capital C, which is called the Chase's coefficient. The dimension of Chase's coefficient is L to the power half into T to the power minus 1. Uh, and this dimension is same as the dimension of root under G, or root under the gravitational constant. So as we mentioned that in pipe flows, the Darcy-Weisbach equation represents a form of a friction or resistance equation. Um, so here we can invoke that equation as well without loss of any originality, and we can actually use that equation by replacing the characteristic length, or the capital D by by the hydraulic radius capital R, and we know that capital R is equal to capital D by 4. So we can replace that in the equation, and we can arrive at the another form of on another form of the equation given by V equals to root under 8G by F into root under R into root under HF by L. So we can see here one very interesting thing, that this equation is looking similar to the Chase's equation, and of course if we can relate the term HF by L as which is the frictional head loss per unit length of the channel, which is also we can also see that, which is also here for a uniform flow, equals to the slope of the total energy line, or SF. So or which again in turn is equal to the channel bottom slope S naught. And if we can write that the coefficient root under 8G by F is equal to capital C, the Chase's coefficient. So this the equation listed in the last shown in the last slide becomes same as Chase's formula, Chase's equation. So thus we can see the analogy between different resistance formula or equations for pipe flows and open channel flow. We also remember that there was this famous popular chart called Moody's chart, which is a graphical representation of the friction factor for pipes, and the friction factor there is plotted against the Reynolds number and the non-dimensional roughness coefficient. Here also, like Moody's chart, we can prepare a chart for the Chase's coefficient capital C, and we can plot that with respect to Reynolds number and another, non-dimensional roughness. So only thing is that in place of the diameter of the pipe, we have to replace the diameter of the pipe by 4 into hydraulic radius, or 4R, in doing so. The equivalent roughness given as symbolized as epsilon s for some common surfaces here shown in the table given below. This lists the equivalent roughness in millimeter for open channels of different surface characteristics, including glass, rough concrete, earthen channels or natural channels, rubble masonry, or untreated gunite. Moving on from Chase's equation, here we discuss another very popular equation, resistance equation for uniform open channel flows. This equation was proposed by Irish hydraulic engineer Robert Manning and is given by capital V equals to 1 by n capital R to the power 2/3 into capital S naught to the power half. This is the equation highlighted in blue and is the first equation of the slide. This, after the name of Robert Manning, is known as the Manning's equation. The coefficient n here is called the Manning's roughness coefficient and is a very important term in the Manning's equation. The dimension of the coefficient is L to the power minus 1/3 into T, and the coefficient is a representative of the channel boundary characteristics. It depends on the roughness of the boundary of the open channel. Capital R is of course the hydraulic radius, and S naught is the channel bottom slope here. Note here that unlike Chase's formula, no derivation is possible for Manning's equation from the very first principles. So we presented a derivation of Chase's formula from combining the momentum equation with the shear stress equation. Here, for Manning's equation, rather, no such derivation is possible. This equation was derived by Robert Manning by comparison of different formula available as resistance formula for open channel flows, and by the process of curve fitting. But due to its simplicity and wide range of applicability for variety of practical applications and very reasonable accuracy, Manning's formula is considered as one of the most popular equations in fluid mechanics of open channel flows, and it's the most widely used practical equation used by practicing field engineers. If we compare Chase's formula with Manning's one, we can see that the Chase's coefficient capital C can be equated to the Manning's coefficient 1 by n by the first equation of the slide, which says capital C equals to 1 by n capital R to the power 1 by 6, which again equals to root under 8g by the friction factor F. Also note that in Manning's equation, the parameters of hydraulic radius or channel bottom slope, those are all measurable quantities. So it's one can measure those quantities in the open channel flow, but the roughness coefficient is a parameter that's typical of the particular channel we're working with, and that has to be estimated quite carefully. So the determination of actual coefficient of roughness value depends on one's experience and judgment, and some typical values are of course some representative values can be given which are derived from extensive experiments, and also some empirical formula are also available for a rough estimation of the coefficient. This formula, the empirical formula we are talking about, they relate the size of the bed particles to the Manning's roughness coefficient. One of this formula is called which is called the Strickler's formula, and which is named after the Swiss hydraulic engineer Albert Strickler, who proposed it. Is the most widely used such empirical formula, and is given by the last equation of the slide, n equals to d50 to the power 1/6 by 21.1. Here d50 is of course the particle size for which 50% of the bed material is finer, and d50 in this equation is has to be used in meters, in the unit of meters. For bed materials with considerable coarse grain fraction, uh, Meir et al. Proposed another equation for the roughness coefficient, which is given as n equals to d90 to the power 1/6 by 26, where d90 is again in meters and is the particle size for which 90% of the bed material is finer. So as we mentioned before, that typical values of the roughness coefficient for different open channel surfaces can be given, which are derived from different experiments. The of roughness coefficient n is given listed in the table below. So this is that's all for the time being. We will continue our discussion on uniform flow in open channels in our coming lectures. Thank you very much.